What happens to nitrogen when you put it in direct sunlight?
I have no idea.
It becomes daytrogen. Like
Oh,
daytime.
no, that's actually your worst yet.
Oh, come on.
Welcome to Field Notes from UW-Madison Extension. I'm Will Fulwider, and I'm joined by my co-host Michael Geissinger. We bring farmers, experts, and agronomists to the table to talk about research-based approaches to the issues facing agriculture in Wisconsin.
We're going to slowly, scale Michael's jokes out of this program eventually with the declining quality therein. But we've got Diane Mayerfeld on the program today. Diane is the Sustainable Agriculture Research and Education Statewide Coordinator for UW-Madison Extension. I've worked a lot with Diane in the past, and excited to have her on today to talk about nitrogen management and climate change. Can you give yourself a little bit of an introduction and talk about kind of what you've been working on?
Sure. Thank you, Will. And thank you, Michael, for the opportunity to talk today. I've been doing this work actually since the mid-90s, so I've been around for a long time, not specifically on climate change, but on sustainable agriculture. And that covers everything from economic sustainability, environmental sustainability, and social sustainability. And we've looked at things like grazing and local food systems and things like that. But it's become clear in the last 3 to 5 years that dealing with climate change is a really, really big challenge for agriculture, as for every other part of our society. And so increasingly, I've been trying to think about that and come up with things that farmers can do.
And there's a lot of money being thrown at it right now with the recent climate smart commodities partnership grants and more legislation passing at the federal level for technical assistance for engaging in carbon credits and the upswing in carbon credits that has been seen for agricultural practices and the such. So there's definitely a rising tide surrounding not just nitrogen management and climate change, but kind of practices geared towards mitigation of climate change from an agricultural level. So it's definitely in the rising tide of things for sure.
Yeah, and it's very exciting. Having been concerned about climate change for a long time, it's wonderful to see that across the spectrum, people are starting to think about what realistic things can we do in this area.
Absolutely. Well, appreciate the introduction and having you on the call today, Diane. And maybe just to kind of kick things off, we keep saying we're going to talk about nitrogen management and climate change, but maybe not everyone understands how those two things could even be related to each other. And so maybe you want to give us a 30,000-foot overview and just briefly describe how nitrogen or nitrogen management on farms is related to climate change.
Thank you. Yeah, that's a great question. Yeah, there are 3 main greenhouse gases. There's carbon dioxide, which is what we hear about all the time. There's methane, and there's nitrous oxide. And so if you look at the US as a whole, CO2 emissions, carbon dioxide emissions, account for about 79% of our human-caused greenhouse gas emissions. And so that's why we all hear so much conversation about carbon. Methane accounts for about 11% of those emissions, and nitrous oxide, which is one form of nitrogen, accounts for about 7% of human greenhouse gas emissions. And if you're doing the math, the other 3% are primarily fluorinated gases like refrigerants. So that's why people talk about carbon all the time. But if we narrow down to looking at the agriculture sector, those proportions change a lot. Nitrous oxide and methane really dominate, and carbon dioxide plays a relatively small role, though it's still pretty important. So if you look across the US, in agriculture, nitrous oxide emissions are 50% account for 50 to 51% of the greenhouse gases emitted by agriculture. Caveat, always, it depends what things you're counting and what things you're not counting. But that's so thinking about it, roughly half of agriculture's emissions are in the form of nitrous oxide. And one of the things to keep in mind is, as we talk about these different greenhouse gases, they each have different qualities. Carbon dioxide is, because it's by far the leading one, is what we kind of use as our standard. And so when we talk about these other greenhouse gases, we compare them to carbon. And when we compare nitrous oxide to carbon as a greenhouse gas, it is way more potent. So one nitrous oxide molecule has around 290 times the warming power of one carbon dioxide molecule. And the other thing we keep in mind when we talk about greenhouse gases is how long they last. And nitrous oxide lasts in the atmosphere. We typically predict it will last in the atmosphere over 100 years.
So it's both more potent and, as far as the warming degree goes, and it lasts longer in the atmosphere than carbon dioxide does.
Yeah, so carbon dioxide, how long carbon dioxide lasts in the atmosphere is actually complicated because some of it's on a very short biological cycle, and we know plants photosynthesize it back into carbon all the time, but some of it can last up there a really long time. It doesn't, when it's in the atmosphere, it doesn't break down on its own. But I think the idea is that the nitrous oxide will actually break down into nitrogen on its own in the atmosphere. But it's important to keep in, and that more potent warming potential takes the longevity of the gas into account as well. So when we use those numbers, that nitrous oxide is 290 to 300 times as powerful as carbon dioxide. That is over 100-year time frame.
Gotcha.
Yeah, and we know too that the atmosphere, sometimes people say the atmosphere is made up primarily of nitrogen, but that's a different type of nitrogen. Do you want to talk about that at all? Or
absolutely, yeah. Again, it's funny. It's about 79-80% of our atmosphere is nitrogen, but that's just an N2 molecule. It's just two nitrogen atoms. And nitrogen, as people probably know, has a complicated cycle. So it's in the atmosphere as just plain most of it is in the atmosphere as just these plain N2 molecules. And then there's, in the sort of in natural ecosystems, some of that nitrogen gets removed from the air by soil bacteria that convert it, and this is called nitrogen fixation, to ammonia. And again, as any farmer listening will know, nitrogen is an absolutely critical plant nutrient, and it's a building block of protein, so it's also a critical human nutrient. So we rely on that. And then in the soil, nitrogen can undergo a whole bunch more transformations caused, again, by other soil organisms. And it can turn into nitrates, which is the best form for plants to absorb it. That's NO3. But it can also, there's a whole bunch of stages that these soil organisms can do. But then it also goes through the next stage, or the final stage in the nitrogen cycle, where other organisms can denitrify it. In other words, break it down into a form where it becomes a gas. It gets emitted as a gas again. And either it gets emitted as N2, which is great, and that's what our atmosphere is full of, but a little bit of it denitrifies to nitrous oxide, which is 2 nitrogen molecules and an oxygen molecule, so N2O. What's
so,
basically,
go ahead, start again.
okay. So that's all part of nature, and a little tiny bit of nitrous oxide in the atmosphere is fine. We need a little atmospheric warming. But what's happened is that humans figured out how to synthesize nitrogen, how to artificially take nitrogen out of the air and turn it into a form that plants can use. And because it's such a limiting nutrient for plant growth, this has been a key factor. These synthetic nitrogen fertilizers have been a key factor in our agriculture and increasing our agricultural productivity. But basically, they've doubled the amount of nitrogen that's, they've added 100% to the amount of nitrogen that would be added to the soils through just natural processes. And so that's also doubled those emissions oxides.
And so when we look at it kind of at the farm level, right? Well, that's an awesome overview. And let's kind of bring it down to how that affects the management or the farmer decisions or at the cropping level. What does that look like, from the farmer's practices? How does that influence kind of this pathway, this process of nitrogen through fixation, through nitrous oxide emissions? How does management affect it?
Yes, well, so as I think I just said, anytime that you're increasing the amount of nitrogen in the soil, you're increasing the potential for nitrous oxide emissions. So fertilizer management and manure management are 2 really critical areas for farmers to focus on. But we also increase the nitrogen in the soil when we have concentrations of grazing animals, or particularly when we have monocultures of legumes like alfalfa. So even though they're, I don't think, as much of a source as our synthetic nitrogen applications and our manure applications, we do need to keep legumes and grazing animals in mind as other potential nitrous oxide sources.
Yeah, absolutely. And would you maybe, so we kind of understand a few of these things and just the amount of nitrogen that's going into systems to be increasing the potential for nitrous oxide emissions. What are some, besides obviously cutting and scaling back nitrogen, what are some potential solutions that we could maybe employ in cropping systems to start addressing some of these issues?
Well, fortunately, I think a lot of good work has been done in connection with water quality, and it's it's great when what we're doing to improve water quality can also be helping our climate. And so they talk about the 4 R's, and you mentioned right rate. So making sure that as we decide how much nitrogen to apply, we make sure we take into account whether manure was applied, whether there were any legumes grown on that soil, any other credits that we might need to consider. And then the other sort of thing people talk about in connection with water quality a lot is right time and putting that nitrogen down when the crop can actually use it. Because nitrogen is very mobile and it will escape in our water and it will escape in our air. And so if we put it down before the crop needs it, there's just so much more chance for it to get into the atmosphere in ways that are damaging and into our water in ways that are damaging. The other thing about timing, and this is where it gets a little complicated, is that for nitrous oxide emissions, if the soil is wet or saturated, it really increases the chance of that nitrogen being converted to nitrous oxide. So you want to avoid application before heavy rain or to saturated soils.
And so kind of for review, we've got 4 R's. The R's are?
The R's are right rate, right source, right time, and right place. And to me, right source is talking a lot about, and I'm going to maybe put Michael on the spot as well, because he probably knows more specifics. I'm not a nutrient management specialist. But, making things like having your fertilizer in a form where it is not as mobile right away. And to me, it's also a little bit a subset of right rate, meaning make sure that you've taken all your credits into account and that you're accounting for them. And so there's right rate, right source, right time. And I talked a little bit about right time, when the plant can take it up. And then the fourth one is right place. And that's talking about putting it where the plant can access it right away. And I think sometimes, and Michael, I invite you to chip in here, it's talking about incorporating it so it's not so liable to run off. But that's where we start to have questions about whether incorporation makes it more accessible to some of those soil organisms that will then convert it to nitrous oxide.
Yeah, I agree with everything that you've already said. With the right source, it's typically the types of fertilizers that we're using. How can we stack that in a way to make sure that it's meeting the crop need as efficiently as possible? But even the right time consideration, there are things that you can do if you're applying, all of your nitrogen up front at the beginning of the growing season to prevent it from getting released early on. And so some of these nitrogen management tools that you hear about in industry, one would be NServe. Function is basically a barrier to those microorganisms to accessing the nitrogen until later. Another strategy to, I would say, minimize the risk of any of that nitrogen being lost either to water or to the air would be just even splitting those nitrogen applications, especially in, when you think about nitrogen management, it often goes hand in hand with corn in particular, I think. But any of these crops that have a high nitrogen need and an inability to fix the nitrogen in the soil themselves. And so I know that splitting those applications can help, increase the amount of nitrogen that's actually available to the plant when the plant actually needs it, especially when you get into July in Wisconsin and you can sit in the cornfield and hear the corn plants growing. It's an important consideration. But
So you talked about crediting and making sure that you're taking the right amount of credits. And I kind of want to drill down on that for a second and be like, how do you know if you're taking the right amount of credits? Is it something you kind of look at a book and say, I applied X amount of tons of manure to this, and therefore it's like that, this amount of credits, or I test my manure? Is it something like you're soil sampling for that even?
Yeah, in Wisconsin and in probably most states that have a significant amount of cropping happening, I'll speak for Wisconsin because it's my experience and where I live and work. There's been a series of research over decades developing these crop need requirements of, so we really know at this point how much like nitrogen, phosphorus, and potassium, for example, we need to grow a corn crop or a soybean crop or an alfalfa crop. And that typically has gone hand in hand with the way that we apply nutrients. What's began changing more recently is the use of a lot of these soil health practices, which intend to kickstart these microbiology biomes. And so what we're trying to figure out right now is, do some of these practices affect potentially the way that nutrients like nitrogen come available to the plant in the soil or not. And I would, some of the more static credits are reliable. For example, a legume credit in Wisconsin would typically be like 90 pounds in the first year. And the manure credits, when you apply manure, we know from the research we've done that some of it's available in the first year, and then the rest of it typically comes available in the second and third year for nitrogen. And so that's where those recommendations kind of come from and are built in. I would say though too that if a particular farm is really interested in what the best nitrogen rate is for their system and the hybrids or varieties they use, the management practices they follow, it can really help sometimes to just set up an on-farm trial and figure out what is the most efficient way, amount of nitrogen for your crop. And in turn, hopefully you can reduce your nitrogen program, which Diane has pitched as a wonderful way to decrease the potential of losing this nitrogen to the environment and the water, to the atmosphere.
But maybe in some cases also helping save some money that people don't have to spend on this input.
Especially with the high cost of nitrogen these days. I think everyone would like to save a little bit of money on that, not use as much. So Michael mentions soil health and the practices that are kind of associated with that. And my mind immediately goes to cover crops. And I'm just wondering, is that a tool that we can use in nitrogen management, Diane? How do we manage those best for nitrous oxide emissions to minimize those?
I think absolutely cover crops can be a tool, and in two different ways. I think one way is that there are cover crops that can be used to hold on to the nitrogen that's there at the end of the season and keep it in the soil. And rye is kind of a classic example of that. The issue with that can be that it continues to hold on to some of that nitrogen early in the season when the corn needs it. But without that crop, people were, that's where, an early small application of nitrogen can make sense. And then as the rye decomposes and releases some of that nitrogen, the corn can presumably use it. But then the other thing is in certain situations, so if you're growing wheat, you can plant a cover crop of, for instance, red clover. You can frost seed the red clover into the wheat, and it can fix nitrogen over the winter. And because it stays alive in the soil, it can substitute for synthetic nitrogen. So I think that can be a very helpful part of the cover crops toolbox as well. So you're not having to take that very energy intensive nitrogen fertilizer and apply it as much.
That's a good call out to our previous episode on frost seeding red clover. So you should go listen to that if you do not know what Diane is talking about. And one thing that I've seen recently talking about cover crops is the fact you were talking about how kind of wet conditions, soil saturated conditions lend themselves to nitrous oxide emissions just because of the process of denitrification. And something I was just reading about, one study there's been several other studies out there, but have shown that winter killed cover crops, such as here in Wisconsin, oats and radishes and the such, can actually lead to higher fluxes of nitrous oxide emissions because you've got this decomposing plant matter, aka this nitrogen, hanging out in really saturated soils of April, March, May time. And it's very climate dependent. This is one study, but it's an interesting kind of tidbit that we need to think about is when we're choosing our cover crops, we need to be choosing them for various different reasons. There's a reason someone plants oats and radishes rather than rye, for example, because maybe they don't want to have to come back and terminate that rye chemically. So there's trade-offs in everything, but those winter killed cover crops are not holding on to that nitrogen to when the corn needs it then in the same way necessarily that others like a red clover that overwinters and doesn't winter kill would be. So, cover crops can be great, but they can also not be as helpful depending on the management strategies there.
Absolutely. And yes, there's so much we still have to learn because this nitrogen cycle is so complex, because the soil biology is so complex, and you get those complexities interacting with variations in soil and climate and weather. And as I said, we still have a lot to learn about specifics, but we also have some basics, and I'll circle back to really making sure that as much as possible, we don't apply more than we need, and that we apply it as much as possible when the plant is using it. Can help move us in the right direction.
And so you were talking about nitrogen cycle is very complex. It is, and we're still learning some, and there's a lot that we don't know, and that's an obstacle in upon itself to figuring out what, the solutions are. But what are some other obstacles to kind of fine tuning these solutions? Is there's other things that we do know that are kind of impeding our efforts?
Well, I just, before I jump into the second part of the main part of your question, I just want to build on, one of the things that adds to our lack of knowledge is that it's actually really expensive and difficult to measure these nitrous oxide emissions. What we do know is that they're highly variable over time. So they vary a lot over the course of the day. And also they vary a lot over the course of the year. So you spoke in the context of cover crops, but that's about spikes in nitrogen emissions when you get these soil thaws. You can also get those spikes if you have, say, fall applied manure and you get a winter thaw. You can have another huge spike, which can be in 24 hours, half of the year's nitrous oxide emission from that place, as far as people can tell. And yet, we don't have good tools for continuously monitoring those emissions. So I think we have a lot, the tools we have are very expensive, and people have to be there and monitor them and actually withdraw those samples of the gases in a little closed chamber that you put on the soil and then test those. So that's one challenge. That's one thing we have to overcome. Other barriers, I think always a barrier is how close to the margin farmers operate. And balancing the desire to be a good steward with those narrow profit margins. And I think lots of farmers would love to experiment with cutting their nitrogen rates or some of these things, but the economic barriers, without some sort of good backstops, I think are also huge.
Absolutely. And longer term, maybe, I don't know, 10, 20 years in the future, how might you think the use of nitrogen on farms, how might you think that will look different in the future? And I have a feeling you might turn it around and ask me too, but I'm curious what your thoughts are on how you think nitrogen management will look different in the future.
Yeah, that's a great question. Well, one of the things you mentioned a little earlier, Michael, is the work on soil health. And there's some really interesting stories coming from farmers who are really on the cutting edge of soil health and regenerative management, who have been able to really reduce nitrogen applications or even eliminate them altogether and still maintain yields. That's not cutting nitrogen out of their system. I think they've got legumes in their rotations. But, if we can learn more about specifically what they're doing right to make that work, and we can disseminate that across the landscape, I think that would be amazing. The other kind of long-term, maybe idealistic vision I have is, we're hearing a lot in the news about our cars switching over to electric cars and the electric fleet. And, I hear that and I'm thinking about right now, something like 35 or 40% of our corn crop goes to ethanol. And corn is nitrogen hungry. You mentioned that, at least here in Wisconsin, that's our big crop that we have to apply a lot of nitrogen to. So does that transition to an electric transportation system offer us some opportunities to maybe even think about what crops we have on our landscape and whether we can shift to things like perennial pasture or just other crops that are less hungry for nitrogen? So those are my two visions, but I am really interested to hear in what you think might change.
Well, yeah, I certainly agree with those, and even the conversation on the ethanol and what could happen with all of that is something that keeps me awake at night sometimes. So I'm glad that you brought that up. I would think too, just generally and very pragmatically, that I think the use of nitrogen is going to continue to go down as we develop, newer hybrids that might be less apt to being as nitrogen hungry as the current ones that we use. Even, and if we are managing nitrogen in the system, I think that 20 years from now, it'll probably be a lot different than it is now. The hope is that it's not more regulated, but I think pragmatically, I think in the future, there'll probably be a much wider use or opportunity to use nutrient management plans on farms to actually map out what the crop needs are for a particular system and reconcile that with the rotations that they use and their different fertilizer sources depending on where they are. And a big part of that too, I think, is setting realistic yield goals. And so the number one probably determinant of how much nitrogen a farmer will apply right now is the amount of yield that they expect to get or the amount of yield that they want to get. And the amount of yield doesn't necessarily correspond to profit margins, which we've kind of already alluded to earlier in the call. But the amount of yield might not even correspond to what the world needs, which is what you alluded to with the discussion on corn, 40% of corn going toward ethanol production right now. And so if I was to spitball, I would say that those are a few of the ways that I think nitrogen management will continue to look different. And, there's a lot of stuff out there right now about these biologicals that are going on. And whatever anyone feels about them in UW or otherwise, I think there is some maybe untapped potential there that, well, why wouldn't it be realistic in, 20 years from now that a corn plant might be able to fix its own nitrogen? Right now, that certainly doesn't really seem to be the case. But I don't know. I don't think it's entirely impossible that our systems could move in that direction. But I would just throw that out there as maybe who knows what will happen. That's part of the fun of this question is we can say whatever we want and it can be totally wrong. But
Nitrogen fixing corn for all is what Michael is saying there.
I actually have a variety in my closet here at home. So
Michael really stepping into his nutrient management position there.
yeah.
That's really great. Well, I think that about does it for us today. Diane, thanks for taking some time and talking with us about climate change and nitrogen management. Appreciate it.
I really enjoyed this conversation. So thank you so much for this opportunity.
Thanks for listening. This has been Field Notes from UW-Madison Extension. My name is Will Fulwider, Regional Crops Educator for Dane and Dodge counties. And I was joined by my co-host Michael Geissinger, Outreach Specialist in Northwest Wisconsin for the Nutrient and Pest Management Program of UW-Madison. A big thank you to Joe Ryan for creating our theme music and to Abby Wilkie-Maki for our logo. If you have any questions about anything you've heard today or about your farming practices in general, reach out to the Extension Agriculture Educators serving your region.